Alright, in this video we're going to be looking at horizontal asymptotes and limits as x approaches infinity. So previously we've encountered vertical asymptotes. So hopefully you've also come across horizontal asymptotes in some of your earlier math classes. But even if you've never heard of them, from the very name itself, the nomenclature itself, I think from there you can make a pretty accurate guess as to what a horizontal asymptote is. Just briefly reviewing, we know that vertical asymptotes are asymptotes that are, as the name suggests, vertical. So if we had an asymptote like this, something that we know is if we had a function, that function can never make contact with this line here, with our asymptote, right? We know that it gets infinitesimally close, but it never actually touches, and this is characteristic of vertical asymptotes. So this is something that we've seen many times so far. But this is actually something that isn't consistent with horizontal asymptotes, which is why I'm bringing it up. For a horizontal asymptote, we're not limited in this same way. For example, if we had an asymptote, horizontal asymptote, again, going something like this, our function, let's assume it's some sort of sinusoidal function like this, you can see it's clearly crossing the asymptote many times, and that is acceptable. Let's say but that the end behavior of this function over here towards the right, it then begins acting more asymptotically, where now this portion gets infinitesimally close but never actually touches, right? That is okay. It's okay if some portions of the function cross the asymptote, while others do not. Whereas when we're looking at vertical asymptotes, no portion of our function can cross the asymptote at any point. So that's something I just wanted to, get out of the way before moving any further. But if we have a graph, I'm sure, we can pretty easily identify horizontal asymptotes. But what about when we're given a function? That's where things get more not super obvious, I think, right? Just looking at a function. So let's look at that. And before, I guess, moving any further as well, I just want to clarify that I may be using the word horizontal asymptote here, but this is also equivalent if I said something like end behavior. End behavior is also just referring to a horizontal asymptote, so these are equivalent. In fact, also if I was saying something like limits as x approaches infinity, all three of these are equivalent. They are synonymous. They're referring to the same thing. So don't ever get confused, or if you ever see on an exam the word end behavior or limit as x approaches infinity, these are all just referring to horizontal asymptotes over here. All right, so now let's look at some of the basic rules here for horizontal asymptotes that we need to keep in mind, right? You want to think of these as rules or tricks. But what does the y value, right, approach as the x value, let's say, approaches negative infinity or positive infinity, right? For vertical asymptotes, we saw that this goes up or down, but our x value is really staying there. But because, again, due to the asymptote. But now when we're looking at horizontal asymptotes, you can see that we're really continuing on to infinity, either in the positive direction or the negative direction. So how do we evaluate this, right? Does it approach a specific number here? Is it growing without any bounds? So the basic rules or tricks here that we should keep in mind for our horizontal asymptotes are going to be these three. Firstly, if we're given a function, again, our functions here, like with vertical asymptotes, are going to have numerators and denominators. So if we're given, these functions are going to oftentimes just be fractions. So if we're looking at a fraction like that, if our denominator, this is important to keep in mind. Really, you just need to use these three tricks. You'll see, again, in application how simple this is. But let me just go on. So we're given a denominator here. And if this denominator grows faster than the numerator, right? What I mean by that, again, if we have, let me complete the statement. So if our denominator grows faster than the numerator, that means that our horizontal asymptote is equal to 0. It's equal to 0. So what I mean by denominator growing faster than numerator is if, for example, we have a small number in our numerator, but our denominator is this huge number here, we can say that then that the horizontal asymptote is equal to 0. Why? Well, just looking at the basic idea of fractions itself, right? Hopefully this is a review, but we know if we have a fraction like 1/10, for example, that's 0.1. 1 over 100, that's 0.01, already much smaller. But what about 1 over 1,000? That's 0.001, right? With fractions, really what we're looking at is, let's say we have a pie, or we have the circle, right, cutting it into 2 or 1/2. These pieces are pretty large. Now into 4, the piece gets smaller. and so on and so forth. So now imagine cutting a pie into an infinite number of pieces, or we're dividing 1 by infinity, or any small number by infinity, right? We can see that that is going to just be 0. That piece is going to be so small that it really is just, it's 0. So because of that, if our denominator is growing very fast and the numerator not as fast, right, that means our horizontal asymptote equals 0. Now what about when our denominator, well, let's say when our numerator and denominator grow at equal rates? If they're growing at equal rates, well then, for example, if you have a big number and then another big number in the numerator, in the denominator, well then this is equal to 1. But actually, more specifically, again, it's going to be equal to the ratio of the coefficients of the numerator and denominator. And so I promise that will make more sense when we look at it, an example problem. I promise it may sound more complicated than it really is. So here it's just going to be the ratio of coefficients. Let's say that. And now the third rule, right? We saw the denominator is growing faster than the numerator. If the numerator and denominator grow at equal rates, that leaves us just with if the numerator, again, it's the same thing here, so grows faster than the denominator, then what happens there? Well, there you're going to have the horizontal asymptote is going to equal infinity. And really what that means, if the horizontal asymptote equals infinity, it means that there is no horizontal asymptote. So if we got something like that, we would just say that there is no horizontal asymptote. So you should internalize these rules, memorize them, whatever, but because we're going to basically be exclusively using these in our problems. So now let's just look at a couple examples then, of different functions, right? If we're supposed to, figure out whether the numerator is growing faster or the denominator is growing faster or they're growing at the same rate, we need to basically be able to recognize which types of functions grow faster as our x values are getting larger and larger. Again, hopefully at this junction in your math education, you're familiar with different types of functions and you can kind of figure that out. But just for example purposes, if we had some sort of polynomial function like x squared, and if we were trying to compare the rate of growth to an exponential function, right, let's say 4 to the x, what's going to happen? Well, let's plug in a 1 here. 1 squared is 1. 4 to the first power is 4. If we put in a 2, that is 2 squared is 4. 4 squared, right, is 16. At 3, that's 3 squared is 9. And 4 to the third power is 64. You can see that this exponential function grows much faster than our polynomial here, right? So again, hopefully this is something that you're able to do or you're able to figure out just generally looking at a function. But just a kind of rule of thumb, if we want to make somewhat of a tier list, we're going to know that our exponential functions, they grow the fastest. They grow very fast. So if you were looking again as an example, this 4 to the x, that's exponential. Another thing we see a lot is e to the x, that's exponential, so it grows very fast, etc. Any of these exponential functions grow fast. Polynomials also grow fast, maybe not as fast as our exponentials, but they're still up there, right? Like, for example, something like x squared, x cubed, 4x to the fifth. This is going to become a big number fast, but not as fast as exponentials. So our polynomials kind of come in second there, but if you want to look at something that grows really slowly, well, that would be your logarithmic functions, right? I'm sure if you've ever seen the graph of a logarithm, you can see that there is growth initially, but then it tends to plateau. So something like ln x, or really just any other logarithmic function there, is not going to grow very quickly. So just keep these in mind. Hopefully, by now, again, you are comfortable with different types of functions, and you have a basic idea of what functions have faster growth versus others. So now let's look at an example, right? Let's say that we have our function f of x is equal to x cubed plus 7 divided by 5x minus 6. So now if we want to basically find the horizontal asymptotes for this function, how do we do this? Well, remember what we have to do is compare the numerator and the denominator. And we can see that in the numerator we have a polynomial, right? X cubed. This other stuff here doesn't really matter. We only need to look at the largest term, or the term that would most greatly affect the growth of the function, right? Sure, x cubed is doing most of the work here. The plus 7 isn't that important. And again, here, 5 to the x, that's the largest coefficient here, right? Here, the x coefficient is 0. Here, it's 1. So we just have to look at the x coefficient that's the greatest. So here, we can clearly see that the numerator has a much faster growth than the denominator does. So if you recall back to our rules, what that means is that we have no horizontal asymptote for this function. And that's really, that's it. That's the answer to this question. It's pretty simple. So now let's look at another one. Let's say that we have our function, f of x, is equal to x plus, or no, let's do 3x plus 4 divided by 5x minus 3. So if we had something like this, again, feel free to pause the video, remember those rules that we talked about, and see if you can answer this question. So if we look at our numerator and denominator, again, the plus 4 here. Oops. Sorry, it's glitching momentarily. Just give me a second. Right, so if we're looking at a function like this, we can see again the 4 plus, the plus 4, the minus 3 is not as relevant. We just look at the largest x terms. So that's 3x and 5x. We can see that those are both linear, or they both have x to the same power, both are x to the first. So that means that this is that second case where the numerator and denominator are growing at the same rate. Again, I know that 3x is different than 5x, but we're talking about on the scale of, again, remember when we're talking about asymptotes, we're just talking about his limit as x approaches infinity. So if I plugged in an infinity there, it's 3 times infinity divided by 5 times infinity. And this is, again, very similar, or it's not going to be insanely, different, at least to the extent that if you had a different power would. So in this case, we're saying that the numerator and denominator have equivalent growth. So what that means is then it's going to be our horizontal asymptote is going to be equal to the ratio of the coefficients. So what that means is the coefficients of this greatest term here. So then our answer is just 3/5. That is going to be our asymptote. This is the answer. Hopefully that's making sense. All right, so now let's look at another problem. Let's say that we have a function f of x that is equal to x plus 7 divided by 4x cubed plus 5. So if we had a function that looked like this, what would be our horizontal asymptotes, or asymptotes? Well, this is going to be that third case, right? Or it's going to be that, which case was it? I don't remember the number, but it's going to be the case where we're looking at our denominator growing much faster than our numerator. I believe that was the first case that we looked at. The first rule, right? So we can see clearly that for the x cubed term is much greater than x alone. So the numerator grows much slower compared to the denominator. And we talked about this, right? If we put something like 1 over infinity, we're taking a small number and dividing it by an extremely large number, our answer is basically going to be 0. So here that our y value, our horizontal asymptote, that is going to be equal to 0. So again, see, so far we haven't had to do a lot of crazy math or anything. We just had to recall those 3 rules or basic properties of horizontal asymptotes, and we were fine. And that's generally the case for most of these problems. So now if we're looking at another function, let's say if f of x is equal to x plus 6 times x minus 2 divided by 6x minus 5 squared. So in this problem, we see that our numerator is in a factored form. So we basically have to evaluate this. But remember, all of these other numbers, the plus 6, the minus 2, they don't really matter here, at least for horizontal asymptotes. So we don't have to waste our time, or we can save ourselves time from truly evaluating this out. We just know that we multiply x to the times x. That's going to be our greatest term. That's going to be our x squared. So that's going to be the greatest for our numerator, and we just need to look at the same thing for our denominator here, right? In order to factor this out, we don't need to square this whole term. We should just square this 6x. and we know that that'll give us 36x squared. The rest is irrelevant. So 36x squared in the denominator and x squared in the numerator. We can see that these terms are of the same magnitude. They're both x squared, which means we're looking at the case that the numerator and denominator grow at equal rates. So we just take their coefficients. Here, this is basically just a 1, and this is a 36. So our horizontal asymptote is going to be equal to 1 over 36. That's the answer. So hopefully this is, making sense for you guys. But moving on to just another type of problem here, or really what we were looking at. Remember, when I'm talking about horizontal asymptotes, we're talking about as limits as x approaches infinity. But x also, again, approaches negative infinity. In the problems that we looked at so far, I didn't really mention the negative infinity here. It was just with infinity, because as it approaches infinity and negative infinity, we would have gotten the same answer, right? But there are certain cases where that's not necessarily true, right? So for example, if we had something with a square root, right, we know that those tend to complicate things a little bit. So let's look at a function. Let's say we have our function y is equal to the square root of 9x squared minus 6x plus 3 divided by 2x minus minus 5. So if we had a function like this, we know, again, we have to see what x approaches as it approaches infinity and as it approaches negative infinity in order to figure out all the possible horizontal asymptotes, right? If x is, we need to see if there's a horizontal asymptote in this direction as well as one in this direction. In the last few problems that we've done, they would have been the same, so we didn't really account for it. But here, that may not be the case. Let's see. So how do we approach this? Just as we have been earlier. But again, we don't really care about this negative 6x plus 3 part. It doesn't really matter. We can just see that the largest term is going to be 9x squared. That's going to be the thing that really varies things the most. And then here we have 2x minus 5. But what we have to do is we don't look at it while it's under the square root. We know that if we take the square root of 9x squared will just be 3x. Again, the rest is irrelevant. So we look at this 3x and we see this 2x minus 5. So these are of the same magnitude here, right? X and x. So then what do? We just take the ratio of the coefficients. So as x approaches infinity, right? This is a positive number. So as x approaches infinity, this horizontal asymptote is going to be 3 over 2. That's the horizontal asymptote. But what about if we were looking at as x approaches negative infinity? What about that? What happens there? Well, the common mistake that students make is that they plug this negative infinity to the simplified form, this 3x, but that is not what you're supposed to do, right? If you plug in the negative infinity to our 3x over here, that would give us the wrong answer. So what we do is we plug in the negative infinity to the x while it is still under the square root sign. So if we plug in negative infinity as x, so negative infinity squared would give us a positive number, and the square root of a positive remains positive, so our numerator is going to be positive. And our denominator, right, if we plug in negative infinity as x over here, that would give us a negative number. And we know that a positive divided by a negative is a negative, so that means that our answer then is going to be negative 3 over 2. So you can see here that we have 2 horizontal asymptotes for this problem. All right, let's look at another problem. Let's look at another example kind of like this, and let's see, how you guys can deal with that or try to figure it out, right? Feel free to pause the video, or rather, I highly recommend you pause the video and give a shot. Give the problem a shot yourself. So let us say that we have this problem here. So if we were looking at this function here, the square root is 16x to the 4th plus 3x minus 4, all under the square root sign, divided by 5x squared plus 1. How do we approach this? So assuming that you've given it yourself, tried out the problem yourself, let's see what the answer would be. Well, again, we don't really care about all this other nonsense over here. Well, not nonsense, but we don't really care about the rest of the function. We just care about the biggest terms here. So that's 16x to the 4th, which we know that under the square root sign, or after we take a square root, would give us 4x squared. And then our numerator is also an x squared term, so we're just taking the ratio of the coefficients here. So in this case, this is a positive number. If you plugged in positive infinity to the fourth remains positive, right? So that means our numerator is positive. We plug in a positive infinity for x squared over here. That still would give us a positive. So we have a positive over a positive as x approaches positive infinity. So there, we're just looking at our coefficients. We get an answer of 4/5. Now, when we're looking at x as it approaches negative infinity, what do we do here? If we plug in a negative infinity here, remember, negative infinity to the fourth is going to become positive infinity, right? Negative infinity squared is positive infinity, times a negative infinity again, and that would be cubed, would be negative infinity, times another negative infinity, x to the fourth, would give us positive infinity, right? A negative number to the fourth power just becomes positive. So this would be positive, so the numerator is positive. And the denominator, right? Negative infinity squared, a negative squared would be positive again. So our denominator is also positive, which means that there is, again, only one horizontal asymptote. It is the same answer. It's going to be 4/5 here. So our horizontal asymptote, again, as x approaches negative infinity, that is also going to be 4/5. So hopefully that's what you got. All right, let's now look at something, right, if we're trying to evaluate the limit. This is, again, just different notation, just really the same exact thing. Remember, I mentioned that something like this is synonymous to whatever we've been looking at so far. If we did something like this, 1/x, for example, how do we do this? Well, let's just start by plugging it in. Let's just do a direct substitution as we always do with limits. If you plug in an infinity, 1/infinity, we know that that is 0, right? So this is -5 times e to the 0. E to the 0th power, anything to the 0th power is 1. So that's -5 times 1, and our answer is -5. So that's not, too challenging. Just got to keep in mind those rules, all the things, all the knowledge we've accumulated over the years is all we're applying here. So now let's say that we have another limit. The limit as x approaches infinity of 3 e to the -x. If we had something like this, what do we do? Well, e to the, or anything to the negative, a negative exponent becomes a fraction, right? So what are we doing here? That becomes 3 times 1/e to the x. Plugging in infinity over here, e to the infinity is a very big number. 1 over a very big number is 0. So this becomes 3 times 0, and our answer then just becomes 0. Nothing too crazy there either. All right, I know this video is getting to be pretty long, so hopefully you stayed thus far. So let's now just look at some trig limits with infinities here. So if we wanted to find the limit as x approaches infinity of sine of x, what would that be? So just take a second to think about that, and we'll go over it together. All right, well, what do we know about sine functions? We know that, again, they're oscillating functions. They oscillate between -1 and positive, -1 and +1. That's what we know about the sine function. So if we're going on for infinity like that, is that changing anything about the function? No, it's still going to just oscillate between 1 and -1, 1 and -1. So what does that tell us? As the limit approaches infinity, as x approaches infinity, well, it's oscillating between -1 and +1, so there is no value there. So that means that this limit does not exist. No real math to do there, just a little background knowledge on the sine function is what we need. That's all. So now let's look at a function. Let's say we're trying to find the limit as x approaches infinity. Let's use cosine this time. So let's say we're trying to find the limit as x approaches infinity of 5 times the cosine of 1/x. If we were looking at a problem like this, how do we approach this? Well, again, it's the cosine of 1/x. So let's just start by trying to do direct substitution. If we substitute an infinity for our x, we get cosine of 1/infinity, which we know 1/infinity is just 0. So 5 times the cosine of 0. What is the cosine of 0? We also know that that's an oscillating function. The cosine of 0 is just 1. So that's 5 times 1, and our answer here is 5. Hopefully you were able to, do that problem. So now let's look at this one last example. Let's say we want to find the limit. This is something that students tend to trip up on as they make a slight mix-up here. Let's say the limit as x approaches infinity of sine x over x. What do we do here? Well, if you remember, this sine x over x, that was one of our trig identities, right? Actually, no. Well, the sine x over x is, but you have to remember that the limit is x approaches 0 of sine x over x. That is our identity. Here, the limit is approaching infinity, so these are completely different. We cannot use this trig identity here. Oftentimes, students remember, oh, the limit of sine x over x, that must be 1. They see the sine x over x, get excited, and say this is 1. But they don't see that here we're approaching infinity, not 0. So if we want to then solve this problem, we just try again, direct substitution. We know that sine is just either 1 or negative 1. So that's just going to be a small number in the numerator. But if we put in a infinity in the denominator, we know that that is huge. So any number, whatever this is, divided by infinity is going to be very small. Or anything divided by infinity is just 0. So here, this is the answer to this problem. The limit as x approaches infinity of sine of x over x is 0. So that brings us to the end of this video. We looked at horizontal asymptotes, limits where x is approaching infinity and negative infinity. Again, and that also is the same thing as end behavior. Those three terms are synonymous. So hopefully you got some use out of this video. It was helpful. You learned a thing or two. If you did, please show your support by liking, subscribing, and leave in the comments any questions you may have or anything you'd like to see next in future videos. And I'll see you in the next one.